49 light-years from Earth, a world exists that defies everything we thought we knew about planets. Scientists call it LHS 1140b. You might call it the best chance we've ever had to find alien oceans. Here's what makes this discovery so unsettling. When astronomers first spotted this planet in 2017, they calculated its size and mass. The numbers didn't add up. The planet was too light for what it should be. Something was missing from the equation. Or rather, something was there that shouldn't exist in those quantities. Water. Potentially more water than exists in all of Earth's oceans combined, concentrated on a world just 70% larger than our own. But that's not the strangest part. 49 light-years sounds like an impossible distance. In human terms, it is. Even traveling at the speed of our fastest spacecraft, the journey would take hundreds of thousands of years. Yet in cosmic terms, LHS 1140b sits practically in our backyard. Close enough that our most advanced telescopes can study it in detail. Close enough that we've already started detecting hints of what might be an atmosphere. Close enough that in July 2024, the James Webb Space Telescope picked up something extraordinary. Nitrogen. The same gas that makes up 78% of Earth's atmosphere. The discovery sent ripples through the scientific community because nitrogen doesn't just appear randomly. It tells a story. On Earth, nitrogen exists in our atmosphere because our planet has been geologically active for billions of years, cycling gases through volcanic activity and biological processes. Finding it on another world, especially one that might harbor oceans, raises questions we're not entirely prepared to answer. LHS 1140b orbits a star called LHS 1140, a red dwarf roughly 1/5 the size of our Sun. Red dwarfs are the universe's underachievers in terms of brightness. This particular star glows with less than half of 1% of our Sun's luminosity. It's ancient, over 5 billion years old, and remarkably calm. Most red dwarfs are violent, throwing off massive flares that would sterilize any nearby planets. LHS 1140 is different. It rotates slowly, once every 130 days, and shows almost no flare activity. That calmness matters more than you might think. When a planet orbits close to an active star, the stellar wind and radiation gradually strip away its atmosphere. It's a slow death sentence. The TRAPPIST-1 system, probably the most famous collection of potentially habitable exoplanets, faces exactly this problem. After years of observation, scientists have found no evidence of atmospheres on any of those 7 worlds. The star destroyed them. LHS 1140b, by contrast, orbits a star that's been quiet for billions of years. Whatever atmosphere it might have had when it formed, it likely still has today. The planet completes one orbit every 24.7 days. That's fast by Earth standards, but remember, it's orbiting a star much smaller and dimmer than our Sun. The orbital distance is only 9.46% of the distance between Earth and our Sun. Yet despite being so close, LHS 1140b receives only 43% of the stellar energy that Earth gets. It exists right at the outer edge of what astronomers call the habitable zone, that Goldilocks region where temperatures could allow liquid water to exist. Could. Not necessarily do. This is where things get complicated, because LHS 1140b is tidally locked. One side of the planet permanently faces its star. The other side exists in eternal darkness. Imagine a world where the sun never moves in the sky, where one hemisphere bakes under constant starlight while the other freezes in endless night. This isn't science fiction. This is the reality for most planets orbiting red dwarfs. On Earth, our day-night cycle distributes heat relatively evenly. Ocean currents and atmospheric winds help smooth out temperature differences. LHS 1140b doesn't have that luxury. The day side could be warm enough for liquid water. The night side would be a frozen wasteland. But here's what astronomers realized when they ran the climate models. If the planet has an atmosphere, even a thin one, heat can flow from the day side to the night side. Not perfectly, but enough to create something remarkable. A twilight zone. A ring around the planet where temperatures hover right at the freezing point of water. Scientists call these eyeball planets because of how they'd appear from space. A dark blue pupil of liquid ocean on the day side, surrounded by white ice extending toward the night side. The resemblance to a giant eye staring into space is both striking and slightly disturbing. Current models suggest that if LHS 1140b has an Earth-like atmosphere, it would host a central ocean roughly 4,000 kilometers in diameter. That's half the surface area of the Atlantic Ocean, except this ocean would be circular, centered on the point where the star sits directly overhead. The water hypothesis emerged from precise measurements. When astronomers first discovered LHS 1140b, they used two different detection methods. The radial velocity method measured how much the planet's gravity tugs on its star, revealing the planet's mass. Transit photometry measured how much starlight the planet blocks when it passes in front of its star, revealing the planet's radius. Combine those two measurements and you get density. LHS 1140b's density was wrong. At 5.6 times Earth's mass and 1.73 times Earth's radius, the planet should have been dense. Really dense. Pure rock and iron dense. Instead, the measurements suggested something lighter. The only substance abundant enough to explain the discrepancy was water. Not surface oceans like Earth has, but water comprising 10 to 20% of the planet's total mass. To put that in perspective, Earth's oceans represent only about 0.02% of our planet's total mass. If you compressed all of Earth's water into a sphere, it would be roughly 1,400 kilometers in diameter. Small enough to fit between the eastern United States and the Mississippi River. LHS 1140b might contain hundreds of times that amount. Possibly thousands of times more water than exists on Earth, concentrated in a world only moderately larger than our own. Where does that much water come from? The answer takes us back to the formation of planetary systems. When stars are born from collapsing clouds of gas and dust, the surrounding material forms a disk. Close to the star, temperatures are too high for water ice to exist. Only rock and metal can condense. Further out, beyond what astronomers call the frost line, water ice becomes stable. The outer solar system is full of it. Jupiter's moon Europa has more water than all of Earth's oceans. Saturn's moon Enceladus shoots geysers of water into space. These aren't anomalies. They're what happens when worlds form beyond the frost line. LHS 1140b likely formed in the outer reaches of its system, where water ice was abundant. Then something happened. Perhaps gravitational interactions with other planets. Perhaps the drag of gas in the early stellar disk. Whatever the mechanism, the planet migrated inward, carrying its enormous water content into the habitable zone. It's a journey that took millions of years and involved the delicate balance. Migrate too far inward and the water evaporates. Stay too far out and it remains frozen forever. LHS 1140b ended up right where it needed to be. But we're getting ahead of ourselves. Before we can talk about oceans and atmospheres and the possibility of life, we need to understand what we're actually looking at. The measurements that revealed this planet's true nature didn't come easy. They required years of observations from multiple telescopes, sophisticated analysis of tiny variations in starlight, and techniques that pushed the boundaries of what's possible with current technology. The story of how we discovered LHS 1140b, and more importantly, how we figured out what it actually is, reveals something profound about the state of exoplanet science. We're no longer just finding planets. We're characterizing them with a precision that would have seemed impossible a decade ago. We're measuring not just their size and mass, but their composition, their potential for atmospheres, their capacity to host the conditions necessary for life. And in the case of LHS 1140b, every new piece of data makes the planet more intriguing. The discovery began with a network of telescopes that most people have never heard of. M-Earth, short for Mini-Earths, consists of 8 robotic telescopes in Arizona and another 8 in Chile. Each telescope is only 40 centimeters across. Small by astronomical standards. But what M-Earth lacks in size, it compensates for with focus and persistence. The project monitors thousands of red dwarf stars, watching for the telltale dip in brightness that signals a planet crossing in front of its star. This technique, called transit photometry, is deceptively simple in concept. When a planet passes between us and its star, it blocks a tiny fraction of the star's light. Measure that dip precisely enough, and you can calculate the planet's size. In 2017, M-Earth detected something crossing in front of LHS 1140. The dip was small but unmistakable. A planet roughly 1.7 times Earth's diameter, completing an orbit every 24.7 days. That discovery alone would have been interesting. Red dwarfs are the most common type of star in the galaxy, and finding planets around them helps us understand how planetary systems form. But the real work was just beginning. Transit photometry tells you a planet's size. It doesn't tell you its mass. For that, you need a completely different technique called radial velocity measurement. The principle here exploits a fundamental truth about orbits. Planets don't actually orbit their stars. Both objects orbit their common center of mass. For a massive star and a small planet, that center of mass lies inside the star, causing the star to wobble slightly as the planet moves around it. Instruments like HARPS, the High-Accuracy Radial Velocity Planet Searcher at the European Southern Observatory in Chile, can detect these wobbles by measuring tiny shifts in the star's spectrum. When the star moves toward us, its light shifts slightly toward the blue end of the spectrum. When it moves away, the shift goes toward red. These Doppler shifts are incredibly small. We're talking about velocities of meters per second. Walking speed. But modern spectrographs can measure them. Multiple teams pointed their instruments at LHS 1140. HARPS. The planet-finding spectrograph at Las Campanas Observatory. The Carmine spectrograph in Spain. Over months and years, they accumulated data. Each measurement added precision. Each observation refined the numbers. The planet's mass slowly came into focus. 5.6 times Earth's mass. Combined with the radius measurement, that gave astronomers something they rarely get for exoplanets: density. Density is where things got interesting. Take a sphere of rock and iron with Earth's composition. Scale it up to 1.73 times Earth's radius. The density should be around 9 grams per cubic centimeter. Maybe 8 if you include some lighter elements. The measurements for LHS 1140 became back consistently lower. Around 5.6 grams per cubic centimeter. That's a problem if you're expecting pure rock. You can't make a planet that size with Earth's composition and get that density. The numbers don't work. Something lighter had to be present in significant quantities. The only candidate that makes sense is water. Not because water is the only light substance that exists, but because it's the only one that's both abundant in planetary systems and stable in solid or liquid form at the temperatures we're discussing. This is where modeling enters the picture. Planetary scientists build computational models of a planet's interior based on what we know about materials under extreme pressure and temperature. You input the mass and radius. The model calculates what combination of elements could produce those values. For LHS 1140b, every reasonable model pointed to the same conclusion: 10 to 20% water by mass. That conclusion fundamentally changed what kind of world we were looking at. The initial assumption had been a super-Earth. Bigger than our planet, but basically the same type of object. Rocky surface. Maybe some atmosphere. The water world interpretation suggested something completely different. A world where water wasn't just present on the surface, but dominated the planet's structure. Think about what that means physically. Earth's oceans average about 3.7 kilometers deep. The Mariana Trench, the deepest point, reaches nearly 11 kilometers. These are surface features on a rocky planet. Now imagine a world where water isn't a surface feature but extends hundreds of kilometers down. Where the ocean doesn't rest on continents but on a rocky core surrounded by exotic forms of ice created under crushing pressure. The pressure at those depths does strange things to water. At around 200 kilometers down, the pressure becomes so intense that water molecules are forced into crystalline structures denser than ordinary ice. This is called high-pressure ice. Multiple varieties exist, each stable at different pressures and temperatures. Ice 7. Ice X. These aren't the ice cubes in your freezer. They form at pressures where water becomes something else entirely while remaining chemically H2O. Below these ice layers, the pressure continues to increase. Eventually you reach the rocky core. But even here, the boundary isn't sharp. Water and rock interact at high pressures in ways we're still trying to understand. Minerals dissolve. Chemical reactions occur that don't happen at surface conditions. The core itself might be partially hydrated, with water molecules incorporated into the crystal structure of rocks. This structure has profound implications for habitability. On Earth, the ocean rests on tectonic plates. Those plates move, driven by heat from the planet's interior. Volcanic activity releases gases that maintain our atmosphere. Nutrients circulate through the ocean via currents and upwelling. The whole system is dynamic, constantly recycling materials. A water world hundreds of kilometers deep doesn't work the same way. The weight of all that water creates pressure that might prevent tectonic activity entirely. Without plate tectonics, you lose the mechanism that regulates atmospheric chemistry over geological timescales. You lose volcanic outgassing. You potentially lose the nutrient cycling that makes Earth's oceans so biologically productive. But here's what the models also show. If LHS 1140b has an atmosphere, even a relatively thin one, heat from the star doesn't distribute evenly. Remember, this planet is tidally locked. One hemisphere always faces the star. The other faces eternal darkness. Without an atmosphere, the day side would be scorching and the night side frozen solid. But with an atmosphere, everything changes. Atmospheric circulation moves heat from the day side toward the night side. Not perfectly. Not completely. but enough to create a gradient rather than a stark divide. The hottest point is directly under the star. Temperature decreases as you move toward the terminator, the boundary between day and night. By the time you reach the night side, temperatures drop below freezing. What you get is a planet partially covered in ice. The night side freezes solid. The ice extends partway into the day side. But at the subsolar point, where the star sits permanently overhead, liquid water can exist. Current models suggest this liquid region could be roughly 4,000 kilometers across. About half the surface area of Earth's Atlantic Ocean. Not enormous by planetary standards, but substantial. This configuration has earned LHS 1140b a nickname: the eyeball planet. From above, it would look like a frozen sphere with a dark blue pupil staring back at you. That pupil is the ocean. The surrounding white is ice extending toward the terminator and covering the entire night side. The eyeball planet concept isn't unique to LHS 1140b. Any tidally locked water world in the habitable zone could potentially have this structure. But LHS 1140b is the first where we have enough data to seriously model what that would look like. The first where the observations matched the theory closely enough to make it more than speculation. Getting to this level of understanding required combining multiple types of observations with sophisticated modeling. Transit photometry gave us the radius. Radial velocity measurements gave us the mass. Those two numbers together gave us density. Density told us water must be present. Climate models told us what that water world might look like if it has an atmosphere. Each piece builds on the previous one. But there's still a crucial question we haven't answered. Does LHS 1140b actually have an atmosphere? All the modeling in the world can't tell you that with certainty. Models show what's possible. Observations show what's real. And until recently, observing exoplanet atmospheres was extraordinarily difficult. Particularly for planets around red dwarfs, where the star's own variability can mask subtle atmospheric signals. That's where the next phase of investigation began. Because in July 2024, a team of astronomers pointed humanity's most powerful space telescope at LHS 1140b and detected something that changed the entire conversation about this world. The James Webb Space Telescope doesn't work like most people imagine. Point it at a planet, take a picture, see what's there. That's not how exoplanet atmospheric detection works. You can't photograph these worlds directly. They're too small, too distant, and completely overwhelmed by their star's light. What you can do is watch what happens when the planet crosses in front of its star during a transit. As the planet moves across the stellar disk, some of the star's light passes through the planet's atmosphere before reaching us. Different molecules absorb different wavelengths. Oxygen absorbs certain frequencies. Nitrogen absorbs others. Water vapor has its own distinctive signature. By analyzing which wavelengths are missing from the starlight, you can determine which molecules are present in the atmosphere. It's like holding a gas between you and a light bulb and watching which colors get filtered out. The challenge is that the effect is incredibly subtle. You're looking for fractional changes in brightness across specific wavelengths. For a planet like LHS 1140b, the atmospheric signal represents a change of perhaps a few dozen parts per million in the total light from the system. Detecting that requires extraordinary precision. It also requires multiple transits to build up enough data to distinguish real atmospheric signals from noise. The team that conducted the July 2024 observations used Webb's near-infrared imager and slitless spectrograph. They observed 2 full transits of LHS 1140b. Each transit took roughly 2 hours as the planet crossed in front of its star. During those transits, the telescope collected light across a range of wavelengths from 0.9 to 2.8 micrometers. That's in the near-infrared portion of the spectrum, invisible to human eyes but perfect for detecting molecular signatures. The first thing they ruled out was a hydrogen-helium atmosphere. If LHS 1140b had retained a thick primordial atmosphere dominated by light gases, that would show up clearly in the transit spectrum. Hydrogen and helium create very pronounced spectral features that are easy to detect. The data showed no such features. That ruled out the mini-Neptune scenario definitively. LHS 1140b is not a gas-shrouded world. It has either a thin high molecular weight atmosphere or no atmosphere at all. But the data showed something more interesting than just absence. There was a subtle spectral feature in the observations that matched what you'd expect from Rayleigh scattering. Rayleigh scattering is the same phenomenon that makes Earth's sky blue. Short wavelength blue light scatters more than long wavelength red light. In an atmosphere dominated by small molecules like nitrogen, this creates a characteristic spectral signature. The shorter wavelengths appear dimmer because more of that light is being scattered away. The detection wasn't definitive. The statistical significance was 2.3 sigma. In particle physics, you need 5 sigma to claim a discovery. In astronomy, the standards are somewhat more flexible, but 2.3 sigma is still considered tentative. It's suggestive. It's intriguing, but it's not conclusive. What made the nitrogen detection particularly significant was the comparison to other possibilities. The team ran spectral retrieval models testing different atmospheric compositions. Nitrogen fit the data better than carbon dioxide alone. Better than water vapor alone. Better than a bare rock surface with no atmosphere. Not overwhelmingly better, but consistently better across multiple analysis methods. If the nitrogen detection holds up under further observations, it would be extraordinary. Nitrogen makes up 78% of Earth's atmosphere. It's chemically inert under most conditions, which means it doesn't easily get locked into rocks or escape to space. On Earth, nitrogen serves as a buffer gas that dilutes oxygen and prevents the atmosphere from becoming too reactive. A nitrogen-rich atmosphere on LHS 1140b would suggest the planet has atmospheric chemistry somewhat similar to Earth's. Not identical, but similar enough to be recognizable. The other critical finding from the JWST observations was what they meant for the planet's overall structure. Remember, the models suggested LHS 1140b could be either a global ocean world or an icy planet with a subsolar ocean. The atmospheric detection, tentative as it is, favors the icy eyeball scenario. Here's why. A global ocean planet with no continents would have very efficient heat redistribution. Water has high thermal inertia and ocean currents would move heat from the day side to the night side relatively effectively. But the spectral data suggested the planet's atmosphere is not dominated by water vapor. If you have a global ocean with an atmosphere exposed to liquid water everywhere, you'd expect much more water vapor than what the observations showed. The eyeball planet model fits better. Ice covers most of the surface. The subsolar ocean is relatively small. The atmosphere above that ocean can contain water vapor, but it's limited to the region directly above the liquid water. Elsewhere, the atmosphere sits above ice. Less surface water means less atmospheric water vapor. The detection of nitrogen without overwhelming amounts of water vapor suggests exactly this configuration. Think about what this means physically. The night side of LHS 1140b is frozen solid. Temperatures there might be 100 Kelvin or colder. As you move toward the terminator, ice gradually thins. On the day side, ice persists until you get close to the subsolar point. Then finally, in that one region where the star hangs permanently overhead, temperatures rise above freezing. The ice gives way to liquid water. The transition wouldn't be sharp. You wouldn't cross a line and suddenly find yourself on open ocean. More likely, you'd see gradual thinning of the ice sheet. Melt ponds forming on the surface. Eventually, enough open water that you could call it an ocean rather than a frozen sea. The exact size of that liquid region depends on atmospheric composition and greenhouse warming. Current models suggest roughly 4,000 kilometers in diameter, but that could be larger or smaller depending on factors we don't yet know. One detail worth considering is atmospheric pressure. On Earth, water boils at 100 degrees Celsius at sea level. But that's at 1 atmosphere of pressure. Lower the pressure and water boils at lower temperatures. On Mars, with its thin atmosphere, water boils at around 10 degrees Celsius. If LHS 1140b has a relatively thin atmosphere, even with nitrogen present, the boiling point of water could be significantly lower than on Earth. That constrains how warm the subsolar ocean can get before it starts evaporating rapidly. The team estimated that if LHS 1140b has an atmosphere similar to Earth's in pressure and composition, the ocean temperature could reach up to 30 degrees Celsius. Comfortably warm by human standards. But if the atmosphere is thinner, temperatures would need to be lower to maintain liquid water without excessive evaporation. This creates a balancing act. You need enough atmospheric pressure to keep water liquid at reasonable temperatures. But you also need the right composition to provide greenhouse warming without turning the planet into a runaway greenhouse. This is where carbon dioxide becomes important. The JWST observations didn't detect carbon dioxide, but they weren't specifically designed to look for it. Carbon dioxide has strong absorption features at wavelengths around 4.3 micrometers. The observations only went up to 2.8 micrometers. You can't see what you're not looking for. Future observations targeting longer wavelengths will search for carbon dioxide specifically. Why does carbon dioxide matter so much? Because it's the primary greenhouse gas on planets like Earth and Venus. A small amount of carbon dioxide can significantly increase surface temperatures through the greenhouse effect. On Earth, carbon dioxide makes up only 0.04% of the atmosphere, but it's responsible for a meaningful fraction of our greenhouse warming. On LHS 1140b, with less stellar heating to work with, carbon dioxide could be the difference between a tiny subsolar pond and a substantial ocean. The relationship between atmospheric composition and habitability is complex. You need greenhouse gases to warm the surface. But too much and you risk runaway warming. You need atmospheric pressure to keep water liquid. But too much and the surface pressure becomes crushing. You need chemical stability so the atmosphere doesn't get stripped away or react with the surface. But you also need some chemical activity to support potential life. LHS 1140b sits in an interesting position regarding all these factors. The star is inactive, so atmospheric stripping is minimal. The planet is massive enough that its gravity helps retain atmospheric gases. The orbital distance provides enough heating to maintain liquid water with moderate greenhouse warming, but not so much that the planet is locked into a runaway state. These are all favorable conditions. But they're not guarantees. You still need the atmosphere to actually be there, with the right composition, at the right pressure. And that's exactly what the next round of observations will try to determine. The team is already planning those observations. And here's where the strategy gets interesting. Carbon dioxide detection requires observing the planet during secondary eclipse, when it passes behind the star from our perspective. During a transit, when the planet passes in front of the star, we see starlight filtering through the atmosphere. During eclipse, we see thermal emission from the planet itself being blocked. These provide different types of information. Transit observations tell us about atmospheric composition through absorption lines. Eclipse observations tell us about temperature and can reveal thermal emission from greenhouse gases. Carbon dioxide emits strongly in the infrared. If it's present in significant quantities, JWST should be able to detect it during eclipse observations at the right wavelengths. The challenge is that these signals are incredibly faint. You're looking for the tiny amount of infrared light emitted by a planet that's already receiving minimal stellar heating, then trying to measure how that light changes when the planet disappears behind its star. It's like trying to measure the heat from a candle at the distance of a nearby city by watching what happens when someone briefly covers it with their hand. Not impossible, but requiring extraordinary precision. The team estimates it will take at least one more year of observations to confirm the nitrogen detection. Then likely 2 to 3 more years to search for carbon dioxide and refine atmospheric models. This is patient work. Each observation requires careful scheduling, because JWST is the most oversubscribed telescope in history. Everyone wants time on it. Every observation must count. But the payoff could be extraordinary. If they confirm nitrogen and detect carbon dioxide, they'll have characterized the atmosphere of a potentially habitable world in detail. That's never been done before. Not for any exoplanet. The closest we've come is ruling out thick hydrogen atmospheres on a few planets. Actually measuring the composition of a terrestrial planet's atmosphere, determining its pressure, identifying its greenhouse gases, that would be genuinely new territory. This is where LHS 1140b's advantages really matter. The star is quiet, so observations aren't contaminated by stellar activity. The planet transits regularly, providing repeated opportunities for measurement. The system is relatively nearby at 49 light-years, making the signals as strong as they're going to get for this type of target. And the planet is right at the edge of the habitable zone, exactly where you'd expect to find interesting climate dynamics. Compare this to TRAPPIST-1, which has gotten far more attention. That system has 7 Earth-sized planets, 3 in the habitable zone. Sounds perfect. But the star is more active, with more frequent flares and stronger stellar wind. Initial JWST observations of TRAPPIST-1b, the innermost planet, found no evidence of an atmosphere. The star may have stripped it away. Observations of other TRAPPIST-1 planets are ongoing, but the active star makes interpretation difficult. Did we actually measure the planet's atmosphere, or are we seeing stellar contamination? With LHS 1140, that question is much easier to answer. The star's inactivity removes a major source of uncertainty. You're more confident that what you're measuring actually comes from the planet. This matters enormously when you're working at the limits of instrumental sensitivity. Every source of noise you can eliminate makes the real signal easier to find. Another factor is the planet's mass. At 5.6 Earth masses, LHS 1140b has stronger gravity than Earth. Surface gravity is roughly twice Earth's. That has several implications. First, it helps the planet retain its atmosphere. Atmospheric escape depends on the balance between a planet's gravity and the energy input from its star. Higher gravity makes it harder for atmospheric molecules to reach escape velocity. Lower stellar activity means less energy driving atmospheric loss. Together, these create favorable conditions for long-term atmospheric retention. Second, higher gravity affects atmospheric pressure. With more mass pulling down on the atmosphere, surface pressure is likely higher than Earth's, all else being equal. Higher pressure allows water to remain liquid at higher temperatures. It also means greenhouse warming can be more effective. The atmosphere is denser, with more molecules to trap infrared radiation. Third, gravity affects ocean depth. On Earth, the average ocean depth is about 3.7 kilometers. But Earth's oceans are shallow relative to the planet's size. They sit in basins on a rocky crust, confined by continental shelves and oceanic ridges. On a water world with no continents, nothing stops the ocean from being much deeper. Models suggest exoplanet oceans could be hundreds of kilometers deep under the right conditions. A 300 Kelvin surface temperature could support oceans 30 to 500 kilometers deep, depending on internal heat and pressure. At those depths, you're not dealing with a surface ocean anymore. You're dealing with high-pressure ice layers beneath the liquid water, exotic forms of ice that exist only under extreme pressure. Ice 7. Ice X. Forms that don't occur naturally on Earth. The internal structure of such a world would be strange. A rocky core, possibly metallic. Then a mantle of high-pressure ice. Then an ocean of liquid water. Then an ice shell at the surface, except where stellar heating keeps it liquid. This isn't like Earth, where oceans are surface features. This is a world where water dominates the entire structure. Geological activity on such a planet would be completely different. No plate tectonics, probably. The ice layers wouldn't behave like Earth's mantle. Heat transport would rely on convection in the ice and ocean, not crustal movement. Volcanism, if it exists, might involve water instead of rock. Cryovolcanism, where subsurface water erupts onto the icy surface and freezes. We see this on some of Saturn's moons. It could be common on water worlds. The subsolar ocean, if it exists, would be the dynamic center of this world. Warmed by the star, possibly fed by cryovolcanic activity from below, bordered by ice sheets that advance or retreat based on atmospheric conditions. It might be the only place on the planet where the surface is truly active. Everything else locked in ice, static, unchanging. But the ocean churning, responding to stellar heating and atmospheric circulation. What would the sky look like from that ocean surface? The star would be fixed at one point, never moving. Always directly overhead at the center of the ocean, lower toward the ice at the edges. The sky would be a dim red, because the star is a red dwarf. Not the bright yellow-white of our sun, but a deep crimson glow. Stars would be visible even during the day, because the star is so dim. The atmosphere would need to be clearer than Earth's to see them, but they'd be there. Fixed in position, like the star. No sunrise. No sunset. No day-night cycle. Time would be measured differently. Not by days, but by orbital periods. One orbit, 25 Earth days, would be the natural unit. But from the surface, you'd never know you were orbiting. The star doesn't move. The stars don't move. Only atmospheric conditions would change, possibly driven by seasonal variations as the orbit's slight ellipticity changes the distance to the star. Weather patterns would be strange. All heating concentrated at the subsolar point. Cold air sinking over the ice, warm air rising over the ocean. Constant circulation from the center outward, then back. Possibly strong winds at the terminator, where warm and cold air masses meet. storms circulating around the ocean's edge, fed by evaporation from the warm center. If the atmosphere is thick enough, those winds could redistribute significant heat. Models suggest that even a relatively thin atmosphere could transport enough heat to expand the habitable region beyond the immediate subsolar point. The Terminator region, where perpetual twilight reigns, might have temperatures just above freezing. Enough for liquid water if the ice sheet is thin or fractured. This creates a gradient. Hot at the center, warm toward the edges, cold at the terminator, frozen on the night side. Life, if it exists, would need to navigate that gradient. Organisms adapted to warm water near the center. Others thriving in cooler regions toward the ice. Possibly ecosystems at the ice-water boundary, where nutrients from the ice meet energy from the ocean. We have analogs on Earth. Hydrothermal vents support ecosystems based on chemical energy rather than sunlight. Polar ice edges host abundant life where cold nutrient-rich water meets warmer currents. A planet like LHS 1140b might combine both environments. Chemical energy from potential subsurface activity, meeting photosynthetic energy in the subsolar ocean. Of course, this assumes photosynthesis is possible. The star's light is dim and redshifted. Earth plants evolved for yellow sunlight. Could photosynthesis work under a red dwarf's glow? Research suggests yes, but it would be different. Red light has less energy than blue or green, so you'd need more of it to drive the same reactions. Plants might be black instead of green, to absorb as much light as possible across all wavelengths. Or they might use different pigments entirely, optimized for red light instead of the broader spectrum Earth's plants use. Ecosystems would be energy limited compared to Earth. Less light means less primary production. Food chains would be shorter, populations smaller. But life is adaptable. Given stable conditions and enough time, evolution finds solutions. LHS 1140b has had billions of years. The star is at least 5 billion years old, similar to our Sun. The planet has likely been in its current orbit for most of that time. If conditions have remained stable, life would have had ample opportunity to establish itself. And that's the theoretical picture. But here's where theory meets observation, and things get complicated. We don't actually know if LHS 1140b has life. We don't even know for certain it has an atmosphere. What we have are hints. Tantalizing suggestions from the James Webb Space Telescope that nitrogen might be present. A 2.3 sigma detection. Statistically significant enough to be interesting, but not definitive enough to publish with certainty. Nitrogen matters. Earth's atmosphere is 78% nitrogen. It's inert, stable, doesn't react easily. Perfect for providing atmospheric pressure without interfering with chemistry. If LHS 1140b has nitrogen, it suggests something survived. Outgassing from the interior, perhaps. Volcanic activity releasing gases over billions of years. Or maybe it's primordial, leftover from the planet's formation. Either way, nitrogen implies an atmosphere thick enough to detect, which is promising. But there's a problem. Red dwarfs are quiet now, but they weren't always. Young red dwarfs go through an active phase. Flares, coronal mass ejections, intense ultraviolet radiation. This phase can last hundreds of millions of years. During that time, any atmosphere on a close-orbiting planet gets blasted. Molecules are ionized, stripped away by the stellar wind. Many planets around red dwarfs lose their atmospheres entirely during this period. LHS 1140 is old and calm now. No significant flares detected. Rotates slowly, once every 130 days. That's unusual for a red dwarf. Most spin faster, generating stronger magnetic fields and more activity. LHS 1140's slow rotation suggests it's aged past its violent youth. But did the planet survive that youth intact? Here's where mass becomes crucial. LHS 1140b is 5.6 times Earth's mass. That means stronger gravity. An atmosphere held more tightly. Harder to strip away, even under intense radiation. Models suggest that planets above a certain mass threshold can retain atmospheres even around active stars. LHS 1140b is right at that threshold. Maybe above it. Compare this to the TRAPPIST-1 system. 7 rocky planets, all potentially habitable. Extensively studied by JWST. Results have been disappointing. TRAPPIST-1b, the innermost planet, shows no signs of an atmosphere. Likely stripped away. The star is more active than LHS 1140, and the planets are smaller, with weaker gravity. They couldn't hold on. LHS 1140b might be different. Larger, farther from a calmer star. If any planet around a red dwarf has managed to keep its atmosphere, this is a strong candidate. Assuming it has, what would that atmosphere look like? The JWST data hints at nitrogen, possibly water vapor, maybe carbon dioxide. That combination sounds familiar. Earth has all three. But proportions matter. Too much carbon dioxide, and you get a runaway greenhouse effect, like Venus. Too little, and there's no warming, and the planet freezes. The balance depends on the carbon cycle. On Earth, carbon dioxide is regulated by weathering. Rain falls, picks up CO2 from the atmosphere, becomes slightly acidic. That rain weathers rocks, which are eventually subducted into the mantle, locking carbon away. Volcanoes release it back. A feedback loop that keeps CO2 levels stable over geological timescales. Does LHS 1140b have plate tectonics? We don't know. It depends on internal heat. The planet is larger than Earth, so more gravitational compression, generating heat. But it's also old, so radioactive elements have decayed, producing less heat. The balance is uncertain. Without plate tectonics, the carbon cycle breaks. CO2 accumulates, or gets locked away permanently. Either scenario is bad for stability. Then there's the ocean itself. If it's really 10 to 20% of the planet's mass, that's an enormous amount of water. Hundreds of kilometers deep, possibly. Pressure at the bottom would be crushing. Thousands of atmospheres. Under those conditions, water doesn't behave like it does on Earth. High-pressure ice forms, even at relatively warm temperatures. Exotic phases like Ice 7 or Ice X. Dense, crystalline structures that sink rather than float. This creates a weird situation. Liquid ocean on top, high-pressure ice at the bottom, solid rock core beneath that. A layered structure unlike anything in our solar system. Earth's oceans are shallow, sitting on top of a solid crust. LHS 1140b's ocean might be so deep it reaches pressures where ice forms regardless of temperature. The ocean floor isn't rock. It's ice. Weird ice, but ice nonetheless. What does that mean for life? On Earth, the ocean floor hosts hydrothermal vents. Superheated water, rich in minerals, erupting from cracks in the crust. Ecosystems thrive there, independent of sunlight. Chemosynthetic bacteria convert chemicals into energy. Entire food chains built on chemistry rather than photosynthesis. If LHS 1140b has a rocky core beneath the high-pressure ice, could heat from that core create similar vents? Possibly. But the ice layer complicates things. Heat would need to penetrate through potentially hundreds of kilometers of ice. That's a lot of insulation. Unless there are cracks, fractures, pathways for heat to escape. Tidal forces from the star might create those pathways, flexing the planet, generating internal friction. But tidal forces are weak on a planet this massive. The star is small, and the orbit is nearly circular. Not much flexing happening. So maybe the ocean is isolated. A vast body of water, cut off from the core's heat, relying entirely on energy from above. From the star. That brings us back to photosynthesis. Can life on LHS 1140b photosynthesize under red light? Theoretically, yes. Red photons have less energy than blue or green, but they're still usable. You just need more of them. Evolution would optimize for efficiency under those conditions. Earth's plants are green because chlorophyll reflects green light and absorbs red and blue. Under a red dwarf, plants might be black, absorbing every wavelength available, maximizing energy capture. Or they might use different pigments entirely. Bacteria chlorophyll, for example, absorbs in the near-infrared, which red dwarfs emit abundantly. Cyanobacteria on Earth use it. An entire planet might evolve similar strategies. Energy would still be limited, though. Less light means less productivity. Ecosystems would be smaller, sparser. But they could exist. Given enough time, life fills every available niche. LHS 1140b has had billions of years. The real question isn't whether life could exist. It's whether we can detect it. That requires biosignatures. Gases produced by life that wouldn't otherwise be present in the atmosphere. Oxygen is the classic example. On Earth, oxygen is produced by photosynthesis and consumed by respiration and geological processes. Without life constantly replenishing it, atmospheric oxygen would disappear in a few million years. Finding oxygen on an exoplanet strongly suggests biological activity. But oxygen is hard to detect. It requires multiple observations, looking for specific absorption lines in the planet's spectrum. JWST can do this, but it takes time. Each transit provides a tiny amount of data. You need dozens of transits to build up a clear signal. For LHS 1140b, that means years of observations. There's another complication. False positives. Oxygen can be produced abiotically under certain conditions. Ultraviolet light can split water molecules, releasing oxygen. On a planet with no ozone layer to block UV, this could happen continuously. You'd see oxygen in the spectrum, but it wouldn't mean life. Distinguishing biological oxygen from abiotic oxygen requires looking at other gases. Methane, for example. Methane and oxygen together is a strong biosignature. They react and destroy each other quickly. Finding both means something is constantly replenishing them. On Earth, that something is life. LHS 1140b's atmosphere, if it has one, might not have oxygen. Life there could be anaerobic, like Earth's early biosphere. Or it could use completely different chemistry. Silicon-based life, for instance, is speculative but theoretically possible. We wouldn't recognize its biosignatures because we don't know what to look for. This is the challenge. We're searching for life, but we're biased by the only example we know. Earth. Carbon-based, water-dependent, oxygen-producing. LHS 1140b might host something entirely different. Something that doesn't fit our templates. We could be looking right at it and not realize. That said, convergent evolution suggests certain solutions are universal. Water is an excellent solvent. Carbon forms complex molecules better than any other element. These aren't arbitrary choices. They're driven by chemistry and physics, which are the same everywhere. Life on LHS 1140b might be strange, but it's probably still carbon-based and water-dependent. The fundamentals don't change. What would change is the details. Metabolism, reproduction, structure. A world with lower energy input would favor slower, more efficient organisms. Growth rates would be glacial by Earth standards. Reproduction cycles measured in years or decades rather than days or months. Intelligence, if it evolved, would think on different timescales. Patient, deliberate, adapted to a world where resources are scarce and change is slow. Of course, we're getting ahead of ourselves. First, we need to confirm the atmosphere. Then characterize its composition. Then look for biosignatures. Each step takes years. The nitrogen detection from 2024 needs verification. More transits, more data. If confirmed, that's step 1. An atmosphere exists. Step 2 is measuring carbon dioxide. That's the next target. CO2 absorption lines are easier to detect than oxygen. If present, it tells us about the greenhouse effect, the climate, whether conditions are stable enough for liquid water. Only after that can we start looking for oxygen, methane, other potential biosignatures. We're talking a decade of observations, minimum. Maybe 2. LHS 1140b isn't giving up its secrets quickly. But that's how science works. Slowly. Carefully. Building evidence piece by piece until the picture becomes clear. The timeline extends further than most people realize. The observations aren't just about gathering data. They're about understanding systematics. Every telescope has quirks. Every detector has noise. Separating real signals from instrumental artifacts requires meticulous calibration. Multiple observations under different conditions. Different orientations. Different temperatures. The spacecraft itself heats and cools as it orbits. Components expand and contract. Electronics drift. All of this introduces subtle variations in the data. You can't just point at a single spike in a spectrum and declare victory. You need consistency, repeatability, independent confirmation from different instruments if possible. LHS 1140b presents unique challenges. Its host star is old and quiet, which helps. But it's also faint. Very faint. That means longer exposure times. More accumulated photons needed to build up signal. Each transit only gives you a few hours of usable data. The rest of the orbit, the planet isn't crossing the star. You're just waiting. For a planet with a 24.7-day orbit, That's a lot of waiting between observations. JWST can't dedicate all its time to one target. It has hundreds of approved programs, thousands of astronomers competing for observing time. Allocations are measured in hours, not days. Getting enough transits to confirm an atmosphere will require multiple observing cycles. Proposals submitted years apart, each building on the last. Meanwhile, ground-based telescopes continue their work. They can't detect atmospheric composition, but they can refine orbital parameters, look for additional planets in the system, monitor the star for flares or activity. Every piece of information helps. Context matters. Knowing the star's behavior over time tells you how stable the planetary environment is. Has it always been this quiet, or is this a recent phase? How much radiation has the planet absorbed over its lifetime? These questions feed into models of atmospheric retention. Whether nitrogen, if confirmed, has been there since formation or accumulated gradually. Then there's the problem of interpretation. Suppose we confirm nitrogen. Suppose we detect carbon dioxide. What does that actually tell us? On Earth, nitrogen is biologically inert. It cycles through the atmosphere, gets fixed by bacteria, returns through decay. But the nitrogen itself isn't produced by life. It's primordial, leftover from planetary formation. Carbon dioxide is similar. Volcanic outgassing, atmospheric chemistry. Life affects its concentration, but doesn't create it from nothing. The biosignatures we're looking for are combinations, ratios, disequilibrium states that shouldn't exist without constant replenishment. Here's where it gets tricky. We don't know what normal looks like for a planet like LHS 1140b. We have no baseline. Earth is one data point. Venus and Mars are others, but they're vastly different. Rocky, dry, hostile. LHS 1140b is supposedly an ocean world, potentially covered in ice except for a central ocean. That's unprecedented in our experience. The chemistry could be completely different. Gases we'd expect might be absent. Gases we don't expect might be common. We're flying blind. Some researchers propose looking for specific markers. Ammonia, for instance. On Earth, ammonia is produced biologically and destroyed quickly by photochemistry. Finding it in an exoplanet's atmosphere would be strange, possibly indicative of life. But ammonia is also produced by geological processes under certain conditions. You'd need to rule those out. Same with phosphine. Recently detected in Venus's atmosphere, initially exciting, later attributed to non-biological sources. Every potential biosignature has to survive scrutiny. Alternative explanations must be exhausted before you can claim biological origin. The real breakthrough would be detecting oxygen and methane together. That's the gold standard. On Earth, methane comes from biological sources and oxygen from photosynthesis. They react rapidly, destroying each other. Both being present means active production. Something generating them faster than they can disappear. That's hard to explain abiotically. Not impossible, but hard. For LHS 1140b, detecting both would require even more observations. Methane has weak absorption features. Oxygen is easier, but still challenging. You'd need dozens, maybe hundreds of transits. Years of data. And perfect conditions. No clouds obscuring the signal. Stable stellar output. Minimal contamination from the star's own atmosphere. Let's assume the best case. Atmosphere confirmed. Nitrogen, CO2 detected. Oxygen and methane found together. Scientists agree it's a biosignature. What then? We found life. Not contacted it. Not understood it. Just detected its chemical fingerprint from 49 light-years away. The implications are staggering. Life exists beyond Earth. It's not unique. The universe is inhabited. But we can't communicate. Can't visit. Can't learn anything beyond what the spectrum tells us. It's a strange kind of discovery. Profound but frustratingly limited. Would it change anything? Philosophically, yes. Scientifically, absolutely. Practically, maybe not. Life on LHS 1140b, if it exists, is irrelevant to daily human concerns. It won't cure diseases or solve climate change. It won't provide new technology or resources. It's pure knowledge. Understanding for its own sake. Some people value that. Others don't. The discovery would dominate headlines for a while, then fade. The work would continue. More observations. Refining models. Looking for other planets around other stars. The search expands. There's another angle. Suppose we don't find biosignatures. Suppose LHS 1140b has an atmosphere, but it's sterile. No oxygen, no methane. Just nitrogen and CO2 in boring ratios. What does that mean? Habitable doesn't equal inhabited. The planet could support life but doesn't host it. Maybe life never arose. Maybe it did but went extinct. Maybe it's there but hasn't evolved to produce detectable signatures. Absence of evidence isn't evidence of absence. We'd learn the planet is habitable, which is valuable. But the big question, are we alone, remains unanswered. The eyeball planet scenario complicates things. If the surface is mostly ice with a central ocean, life would be confined to that ocean, potentially deep below the surface, insulated from the atmosphere. Biosignatures might not reach detectable levels. You'd have organisms producing gases, but they dissolve in water, react with minerals, never make it to the air. We'd see a habitable planet with no signs of life, even though it's teeming below. This is the problem with remote detection. You're limited by what reaches the surface and escapes to space. Some scientists propose looking at reflected light instead of transmitted. During the planet's orbit, it reflects starlight. The spectrum of that reflection carries information about the surface. Ice, water, rock, vegetation, each has distinct signatures. Vegetation, for instance, reflects strongly in near-infrared. The red edge. On Earth, this is detectable from orbit. Forests, grasslands, they light up in IR. If LHS 1140b has photosynthetic life, maybe we'd see it. But the signal is faint. Requires the planet to be bright, not tidally locked with one side in darkness. And vegetation is a huge assumption. Photosynthesis might use different pigments, different wavelengths. We'd miss it entirely. Technology is advancing. Future telescopes will be more sensitive. Larger mirrors, better detectors, longer observation times. The extremely large telescope, under construction, will dwarf current instruments. Direct imaging might become feasible. Blocking out the star's light, photographing the planet directly. Analyzing its spectrum without waiting for transits. That's decades away for a planet like LHS 1140b, but possible. Each generation of instruments brings new capabilities. Questions unanswerable today become routine tomorrow. In the meantime, LHS 1140b sits there, orbiting its dim red star, potentially covered in ice, potentially hosting an ocean beneath, potentially harboring life we can barely imagine. It doesn't care about our telescopes or our theories. It just exists. A world following physical laws, indifferent to whether we notice. The significance is entirely human. Our curiosity, our drive to explore, our need to know if we're alone. LHS 1140b is a mirror. What we see in it reflects what we're looking for. This is the state of exoplanet science. Tentative detections, years-long observation campaigns, careful interpretation, always aware of limitations. It's not dramatic. No eureka moments. Just incremental progress. Data accumulating. Models refining. Understanding deepening slowly. The answer to whether LHS 1140b hosts life won't come tomorrow. Probably not next year. Maybe not this decade. But the work continues. Telescopes point skyward. Photons trickle in. Spectra build. And someday, we'll know. So where does this leave us? We have a planet 49 light-years away that might be covered in water. We have tentative hints of nitrogen in an atmosphere we're not completely sure exists. We have models suggesting an ice-covered world with a central ocean, staring back at us like a frozen eye. We have a decade of observations ahead before we know anything definitive. That's the honest answer. Not satisfying, but accurate. LHS 1140b represents something specific in the search for life beyond Earth. Not the first potentially habitable planet we've found. Not the closest. Not the most Earth-like by most metrics. But possibly the most observable. The one where stellar activity doesn't obscure atmospheric signals. The one with enough mass to retain an atmosphere against radiation. The one whose geometry, tidally locked and transiting, makes it accessible to our current technology. It's a target of opportunity. A planet that happens to be in the right place, around the right kind of star, at the right distance from us. We didn't choose it. The universe offered it, and we're taking advantage. The eyeball planet concept is almost too perfect. Too visually striking. A frozen sphere with a blue pupil staring into space. It's the kind of image that dominates press releases and popular articles. But strip away the metaphor and what remains is stranger. A world where one hemisphere never sees its sun. Where ice extends across most of the surface. Where liquid water, if it exists, occupies a small region locked beneath a stationary red star. Where weather patterns would be driven by the temperature gradient between eternal day and eternal night. If you stood on that ocean, you wouldn't recognize anything. The sky would be wrong. The star unmoving. Time measured not by sunrise and sunset but by whatever periodic processes the planet system produces. Maybe orbital variations causing slight temperature changes. Maybe atmospheric cycles unrelated to daily rotation because there is no daily rotation. Life there, if it exists, evolved under completely different constraints than Earth life. Lower energy input. No circadian rhythms tied to day-night cycles. Potentially confined to a small habitable region surrounded by hostile ice. Everything slower, more conservative, adapted to scarcity. We're not looking for aliens with technology. Not searching for radio signals or megastructures. Just chemistry. Molecules in an atmosphere that suggest something is producing them faster than they should disappear. That's the bar. Chemical disequilibrium. A planet that's out of balance in ways that require biological explanation. Even that might be beyond us for now. The nitrogen detection is tentative. Carbon dioxide hasn't been confirmed. Oxygen and methane remain theoretical targets. Each observation pushes the timeline further into the future. 1 more year to confirm nitrogen. 2 or 3 more to search for CO2. Then years more for biosignatures. All of this assuming perfect conditions, no instrument failures, continued funding, sustained scientific interest. The reality is that most exoplanet observations fail to find what they're looking for. Not because the features aren't there, but because detecting them is impossibly hard. You're measuring fractional changes in starlight after it's traveled 49 years through space. Tiny signals buried in noise. Systematic effects from the telescope itself. Stellar variability. Atmospheric contamination from Earth if you're using ground-based instruments. Every observation is a battle against uncertainty. LHS 1140b might have an ocean. It might not. It might have life. It probably doesn't. But it's the best target we have for answering these questions with current technology. That makes it worth the effort. Worth the years of observations. Worth the careful analysis and cautious interpretation. The comparison to TRAPPIST-1 is instructive. That system got enormous attention. 7 planets. 3 in the habitable zone. It seemed perfect. Then observations revealed the star's activity had likely stripped the atmospheres. Years of telescope time invested, and the result was negative. Not wasted, we learned something important about atmospheric retention around active red dwarfs. But disappointing. LHS 1140b might be different. The quiet star improves the odds. The massive planet helps retain whatever atmosphere exists. The geometry makes observation feasible. These aren't guarantees, but they're better conditions than most exoplanets offer. What's certain is that this planet exists. Right now, as you read this, it's completing another orbit. 24.7 days. Regular as clockwork. Whatever's happening on its surface, ocean or ice or something we haven't imagined, continues whether we observe it or not. The universe doesn't wait for our understanding. 49 years from now, light leaving LHS 1140b today will reach Earth. Someone might point a telescope at it. Technology we can't imagine yet. Sensitivity that makes JWST look primitive. Maybe they'll have the answer. Maybe they'll know what we can only speculate about. Atmosphere, ocean, life. Or maybe they'll still be gathering data, still waiting for enough observations to draw conclusions. The search for life beyond Earth operates on timescales longer than careers. longer than individual missions. Projects started by one generation of scientists get completed by the next. LHS 1140b is part of that continuum. Not an endpoint. A step. One planet among thousands will eventually characterize. Each adding to our understanding of what's possible, what's common, what's rare. If we find life there, it changes everything and nothing. Philosophically profound. Practically irrelevant. We can't visit. Can't communicate. Can't do anything except know it exists. But that knowledge matters. It answers the question that's driven astronomy since humans first looked up. Are we alone? Just knowing the answer, even from 49 light years away, would be enough. And if we don't find life, that's data too. A habitable planet without inhabitants. Constraints on where life can arise, how often, under what conditions. Negative results inform the search as much as positive ones. Every observation narrows the possibilities, clarifies the picture, moves us closer to understanding. LHS 1140b will keep orbiting its star. We'll keep watching. Data will accumulate. Models will improve. Observations will continue. And eventually, probably years from now, we'll have an answer. Not the answer we hoped for, necessarily. Not the one that makes headlines. But the one that's true. The one the universe gives us when we look carefully enough. That's all we can do. Point our instruments at distant worlds and see what they reveal. Sometimes the revelation is profound. Sometimes it's mundane. But every observation teaches us something. Every spectrum adds detail. Every transit refines our understanding. Science doesn't offer certainty. It offers increasingly accurate approximations. Better questions leading to better answers leading to questions we couldn't have asked before. Right now, LHS 1140b is the best place to look. The most promising target for finding something extraordinary. An ocean world around a quiet star, close enough to study, strange enough to matter. Whether it delivers on that promise remains to be seen. But we're looking. That has to count for something.
Look at the waistcoat.
Likes the video, own the t-shirt. Simply follow the link in the description below for this and more.